Last time we looked at the kinematic equations derivation for the two displacement equations. We've got this one here, d equals vit plus half at squared, and d equals vi plus vf over 2 times the time. One of those was the Trapezium Formula for the area under the graph of velocity against time. Let's just quickly sketch that out for reference. The other was splitting the area under the graph up into two sections and just taking the area and adding them together for each of those two sections. So this time we want to look at the other two equations. First of all, we will look at Vf equals Vi plus At. This is a relatively simple one. On the graph, that point there is Vi, and then your final point across here, that's Vf. So very simply, the final is going to equal the initial plus whatever the change in velocity is. Okay, makes sense. You start off at one point, whatever the change is, you add that change to the starting point and you get the end point. What we want to show is that AT part is equivalent to delta V, and we can do that from the acceleration equals change in velocity over the change in time. If we rearrange that, we saw the same equation in the previous video. I recorded it yesterday, so if I talk about yesterday, that's what I mean. So you can see that delta V equals A times delta T, or if we're just dealing with T as a time rather than a change in time, it's basically the same thing, it's just a matter of notation. So delta V equals AT, and we substitute AT into there, and we end up with exactly what we want over here. Vf equals Vi plus At. Now, the second one is just a wee bit more complicated, just a tiny bit more complicated. How we derive it is by using two equations and substituting one equation into another. You can have a bit of a go at that yourself, stop the video and just go right ahead, but I'll have a go at doing it now as well. And you'll notice that each of the kinematic equations has one variable missing from it. That's the beauty of these kinematic equations. If you have an unknown, it doesn't matter because, if you have two unknowns in the situation, it doesn't matter because any one of the equations can eliminate one of those unknowns so that you can still solve. For instance, the very first one makes no mention of the final velocity. So if you don't have the final velocity, but you need to find the displacement, then you can still use that. This one has no displacement part in it, and this one has no acceleration part in it, and the last one, which we're about to look at now, has no time factor in it. Okay, so let's have a little look at how we're going to do that. Easiest way, I think, this is not going to be that wonderful, but we'll give it a go. If we take Vf equals Vi plus At, and if we remember, this last equation has no time factor in it, so we want to rearrange this for time and then substitute it into another equation. So I'll actually use these two equations underlined in green. So the second equation is d equals Vi plus Vf divided by 2 times by the time. So I'm going to rearrange this equation for time and substitute it into this equation. So let's just have a bit of a go at that, give ourselves a little bit of space to work with, and always like choosing nice colours. It's a lot of fun, stimulates your creativity and your lateral thinking and all that kind of stuff. So let's rearrange the first equation. Vf minus Vi equals At. If we divide both sides by A, then we can cancel out there and we have T equals Vf minus Vi over A. Let's just write that. Oops, that wasn't meant to do that, but let's write that kind of clearly here. T equals Vf minus Vi over A. And I'd like to put brackets around them so it's a little bit easier to see what you're doing when you substitute in that value for T into this equation. So, getting it a little bit tricky. Let's just make that smaller and out of the way. One more colour once again. Blue. So let's rewrite the new equation with T substituted in. D equals Vi plus Vf over 2 times, and we'll put brackets around that just to separate it, times by Vf minus Vi over A. Okay, this looks kind of horrific, but don't panic because we can take a couple of relatively simple steps to start off with. We can multiply both sides by 2, and we can multiply both sides by A, which should eliminate our two denominator parts of the equation. So if we times by 2A, that means the left hand side is 2AD. You can already see that part of the equation coming out, and we've got Vi plus Vf with the 2 part cancelled, and Vf minus Vi with the A part cancelled. So now we've got a little bit of a tricky part. We have to multiply out these two brackets, and remember, every one thing in one of the brackets you have to multiply out in the other. So this part here has to multiply to that and to that, and then the same thing, this part here has to multiply to that and to that. So let's get stuck into that. 2AD for continuity equals Vi times Vf minus, because we've got the minus Vi term, Vi squared. And giving ourselves a wee bit more space, we've got, for the second part of the term, we've got plus Vf squared, and then we've got minus Vf Vi. Now, till these terms are the same, this term here, minus Vf Vi, and this one, Vi times Vf. It doesn't matter the order of the terms. One of them is positive and one of them is negative, so that's going to cancel out. And we're going to leave you left with all of the parts that we need for our equation. So let's just go right through to the end. Go back to my favourite purple colour. We've got 2AD equals V negative, don't lose that, Vi squared plus Vf squared. And we're trying to come up with an expression for Vf squared, and you can see this is going to rearrange nicely. Vf squared equals, we're adding Vi squared onto the other side, so it's positive Vi squared plus 2AD. Okay, so that's the whole process. Hope that's helpful for you, and please share these videos with everybody. And if you do so, you will make me a very happy teacher. Thanks very much.